All right, so as we go through, there's optimize means maximize or minimize. So that's a maximum, minimize. And you want to make sure that's the equation that we work with to get the first derivative of when it's all said and done. Because we're going to come up with two equations. All right, only one of them do we want to take the derivative of. And that's the whatever you're trying to optimize. Are you trying to maximize the area? Are you trying to minimize the perimeter? Whichever one you're trying to do that to, that's the function you take the derivative of. Step number 3, we need to write your equations in terms of a single variable. Again, thinking about when we write the area equation, length times width, we have two different variables. So what we need to do is once we write our two equations, the equations that's not being optimized, that we're taking the derivative of, we need to resolve that for a letter so that when we substitute it into the one we're taking the derivative of, we only have one variable. Okay, that way we don't have to do implicit differentiation stuff. Okay, we're not intended to do that in this section. Once we get done with rewriting, then we go through and do our derivative, figure out our x values to where a max or a min could occur, test it, okay, and then determine the domain or the endpoints of your equation to verify the endpoints represent a max or min. So that kind of pulls us back to when we were testing on a closed interval, and we're testing the a and the b values as well with the potential critical points. You know, when we tested all the things where it was made as does not exist or equaled 0 in the derivative, and then we tested the closed interval endpoints, and we said, okay, where is the absolute max? Well, who had the biggest y answer, and that was the absolute max. So it's going back to doing that. That's what they're reminding us in step 5. Not only do we test what we get from the first derivative, we got to test the endpoints too. Because the endpoints could be the length of one of the sides to help maximize or minimize what we're looking for. Okay? So that's what that's saying is don't forget to use the endpoints to do that. So here we go. Find two numbers whose sum is 30 and whose product is as large as possible. So first off, we go as follows. Two numbers whose sum is 30. X plus y equals 30. Their product is as large as possible. So product, well, that would be equal to x times y. And this telling us here, this stage here, product as large as possible, that means we're trying to maximize the product. Which tells us that as we go forward, we want to take the derivative of the product equation. Okay, that's what we want to take the derivative of. All right, so now all we've done right now is we've written our two equations. We know eventually I need to figure out product prime. I need to figure out product prime is what I got to figure out. But before I can do that, I need to rewrite it to where there's just one variable, not two different ones. I need one variable. So we go back to the first equation and say, you know what? Pick. Do you want to do it in terms of x or do you want to do the derivative in terms of y? In terms of x, okay? I like that idea. So let's subtract the y over. So let's subtract the y over. We get x is equal to 30y, and Mr. Stevens just did the wrong thing. How many of you subtracted the x over? Because that's technically, well, we can do it this way since you already wrote it. Since you follow me off the bridge anyway. We just do it this way. So, misery loves company. So I'm going to rewrite my equation as, since that's going in for x, we have 30 minus y times y. There's my new product equation over on the right-hand side. Again, it would look the same just with x's if we did it the other way. So it's not going to be that much of a difference. Go ahead and distribute. So our new product equation is 30 minus y squared. And so that's our new product equation. And then now what we want to do is we want to go ahead and, again, this is where they wanted you to stop on this worksheet. They wanted you to stop here and then go forward. First question. Oh, I forgot it. Sorry, I talked about it, didn't do it. Thank you. I bet you two had the same thing. Sorry. The y does go on that 30. It does get distributed. Again, this is where they wanted us to stop. Okay, they wanted us to stop right here and then move on to the next problem with this lesson is what they want us to do. We technically can go on to step number 4. I can go ahead and figure out what product prime is. I can go ahead and figure out what my product is. So what is product prime? Well, that would be 30 minus 2y. Just take the derivative of that right-hand side. And then now we would go through and say, all right, I want to find out where are my critical points. So set it equal to 0 and solve. 0 is equal to 30 minus 2y. Add the 2y across. Again, I still see you guys occasionally making goofy mistakes and just automatically separating the two but not doing an operation, so you're off by your negative values on your stuff. So y equal to 15 is, I think, a potential maximum. So with that in mind, let's go to a number line. Put 15 in there. And then now we just test points. For it to be a maximum, and this is going to be a challenge one, because again, they didn't really want us to go all this way with it. We don't have endpoints where they tell us between 0 and something. We do have to do whole numbers. But if we say, all right, let's pick a number. They didn't tell us they had to be both positive and so forth, but it is a length of a, it's not a length of a side, so we're okay. So if I choose, let's say 10, what is f prime of 10 and what is f prime of 20? Let's test to see where is it positive and negative, and does this represent a max or a min or whatever. So as I do that, if I put 10 into the derivative, 30 minus 20 would be 10, so that side is positive. And then on the other side, we would put 20 in, we get 30 minus 40, which is negative, so that is a max. Now, we don't have endpoints to be able to test them, and that's what they wanted us to do in the process of step 5 is, hey, if we got a closed interval, make sure you test the endpoints. Okay, so this is telling us that if we use 15 as our y value, then that's going to help us find the maximum product with whatever x value corresponds to it. Well, in this case, if y is 15, what does x have to be? X has to be 15 too, right? If I know y is 15, can I come back to this first equation up here and say, well, what's 30 minus 15? If I do 30 minus 15, that tells me that x has to be 15. And so what's my max product? What's my max product that I could get? What's 15 times 15? 225. Remember, us 8th grade teachers made you guys memorize some perfect squares. Okay? All right, so again, that's just taking you through the steps in the process. We write the equations, figure out which one we need to maximize or minimize, which is optimized, is the generic way. Then we need to rewrite it so there's only one variable. Then we take the derivative, continue what we've been doing for this chapter, find the critical points, make sure we test endpoints as well, and so forth. This one just didn't have any endpoints. So question number 2, it says the point on the graph y equals the square root of x. What point is closest on the graph to that point 50? All right, now eyeballing it, wouldn't you say it's probably somewhere in that zone that I marked in orange? Wouldn't you think it's roughly somewhere in there? We know that the origin's way too far away. Okay, and as I passed 50, I start getting further away. So somewhere in that zone, I know there's a ordered pair that is the closest on that graph to that point right there. And we want to try to figure out, well, what is it? Okay, by using calculus to help us figure that out. Okay, so let's do this as follows. Somewhere, and let's use I'm going to use pink. Somewhere on this, I'm going to put a dot just right there, just somewhere. There's a dot. Well, how do we label that dot as an ordered pair? It's x comma what? What would be the ordered pair generically for that location? What'd you say? Yeah, root x. Yeah, generic. Because if I told you x was 4, then what would you say for the y value? Yeah, 2. You'd square root it, okay? So the ordered pair, any ordered pair on that graph, technically its generic format is x comma square root of x, is any ordered pair on the square root graph thing. So again, we need that to help us go forward, okay? We need to generically represent that point that we're trying to find. All right, so now I'm trying to find the distance between those 2 points. I want it to be as small as possible. I want that distance to be closest. That means I want to minimize. Closest in this case means minimize. So that means I'm searching for a minimum value is what I'm searching for. Okay, the smallest value. Okay. Now, do you remember the distance formula? Square root x values squared, subtracting the 2 x values, and then add the difference of the y values squared. So here is your generic format. I'm just going to put it in generically. Again, it doesn't matter what order. You can mix up the order when you're doing the distance formula, because once you square the stuff, it's always positive inside there. So, slope, we had to be careful that whoever we started with on top had to start first on the bottom in order for us to be okay with the signs as we were doing things. But for distance formula, it doesn't matter as long as you subtract the 2 x's and squared and you subtract the 2 y's and squared, then it's okay. So, all right, fair enough. They do give us an ordered pair to work with. They gave us 5, 0. And we now have our generic location up above. And so as I now fill in, I can start filling in this and saying, all right, d is equal to the square root of, again, doesn't matter which x value you start with. We can technically just say x minus 5. As long as you subtract the 2x values, you're fine, square it, plus subtract the 2 y values, square root of x minus 0 squared. Now, by me rewriting the generic ordered pair in terms of the y values in terms of x already, we skipped one step. Because typically we would have said like, hey, any ordered pair on there is x comma y. And so we would have been in trouble once we put in here, we would have had y minus 0. Like if that's your first way of writing something, it was like x comma y. And we would have had like y minus 0. So here we would have to figure out that, oh, well, to find the y value on that graph, we just take the square root of the x value. So we just did one step a little bit sooner and stuff when we found what y was in terms of x is what we did a little bit earlier. Okay, so now we don't have to put it in. We've already got it that way. We could clean it up. You can square out the stuff. You don't have to. All I'm going to clean that up, and I'm going to say it's the square root of x minus 5 quantity squared plus x is what I'm going to clean it up as. Now, on the next page, we'll actually find the points, okay? Because we'll pull this formula, what we have there, on the next page, and we'll have more room to show all of our work to find this stuff, okay? So this is now primed for us to find d prime, and it's ready for us to find the x values so that we can go about doing what we need to do, okay? Let's go through number 3. We'll finish up some of these of the writing, then we'll skip over to 5.11 and actually solve out the rest of the ones they want us to solve out, okay? Mr. Kelly needs to make an open top box. This is a typical question in calculus. He has a piece of cardboard paper that is 14 by 30. To do this, Mr. Kelly cuts out squares of equal size from the 4 corners so that the 4 sides can be bent upwards. What size should the squares be in order to create a box with the largest possible volume? I want to maximize volume. I like writing that down there so it reminds me that I need to create a volume equation with the same variable in it that's I'm going to take the derivative of. Okay, so that's before we start doing stuff. I like writing down what am I doing and with what equation do I need to do the derivative of. All right, so again, generic rectangle. volume equals length times width times height. That's just generic. All right? So now we have to go through and say, all right, let's draw a picture. This one, a picture may help us. I got a rectangle. Each of the corners, we're going to cut out a square in each of the corners that are x by x. And we know it is 30 by 14. Well, if I cut out the squares and I fold up the edges, what's the height? What letter? Instead of being h in the formula, but technically, based on our picture, what's the height represented with which letter? If I cut out each of these squares and I fold the edges up, fold up this edge, fold up this edge, fold up this edge, fold up that edge, what represents the height technically in this problem? What letter? It's just x, isn't it? If I fold up this right side, if I fold that side up and I look at it, on the side view, my height is right here, which is basically the length of whatever I cut out on each of those parts. Okay? So the height is going to be x. Now we have to go through, so that lets us know that we need to change our length and our width to have x as part of its variable. So length equals 30 minus 2x. Width is equal to 14 minus 2x. Now, why did I do 2x? Yeah, I'm cutting x out of each side. I'm going in here, and on the length side, which is 30, because we always think length is like the biggest sometimes, but if this is 30, I'm cutting out x from this side out and x from the left side out. And that's really the length of this edge here of the box now that we're going to actually see is basically 30 minus 2x. And we do the same thing on the other side too. And so now, as I rewrite my volume equation, volume is equal to 30 minus 2x, 14 times 14 minus 2x, times x. Now, we don't want to take the derivative yet. We want to clean this sucker up. Okay, just because we don't do a product rule with three things. Okay, we have to, you could distribute the x to one of them and then do the product rule. It might be easier just to go ahead and FOIL the whole thing out and just get it so you can use the power rule the whole time. I would think, would be the easiest. So with that in mind, this is volume equals 30 minus 2x times 14x minus 2x to the squared. And then now 30 times that, isn't that 420? 3 times 14 is 42, so 320x, and then it would be 60x squared and 28x squared, which would be minus 78x squared, and then is it plus 4x cubed? Did I do that right? Oh, do I need to wait a second? Double check my foiling. I think the middle number may be off for base what I copied down earlier. Is the middle number 88? 88 in the middle. Thank you, bud. I don't always like looking at my notes over there because when I look over to what I wrote down physically, then I start losing track of what I've said and where I'm at. And sometimes I use those as a guide, but I don't like reading them like a politician off of a teleprompter because it messes me up when I look at them too much. Get me off the train of thought and talk. Now, what we could do, we could go through and take the derivative, and we could find out our x values and figure out, okay, what does x need to be for cutting in off the corners to cut off on the corners from the things in order to help us maximize the volume of that box. Okay, is what we can do. Okay. Let me look to see if it's on the next page. It might be, because if it is on the next page, then we'll do it there. No, there's the wire problem. There's that problem. Let's go ahead and do it. Because we only have 3 practice problems on the next page, so we might as well practice since this was an easy one to work with to find what does x need to be. All right, so let's find v prime. Okay, remember, this is not velocity. It's volume. Okay, it's volume. So 420 minus 176x plus 12x squared. So 0 equals 420 minus 176x plus 12x squared. I would divide everything. Is everything divisible by, we know they're all even. That's why I may take it down that way. If I divide through by 2, that gives me 0 equals 210 minus 88x plus 6x squared. So those are still all even, so I can divide by 2. So that is, isn't that 155? Isn't 210 divided by 2 155? Yeah. Okay, thank you. Minus 44x plus 3x squared. Again, I like factoring. That's my go-to. If it factors, I know it's going to be a 3x. It's going to be a 3x in some form of what? Where? Oh, 105, 150. Okay. Thank you for checking, because I was going to really rack my brain on that one. All right, so let's change that. Thank you, Bubs. I just said that out so fast it sounded like it. There we go. All right, so we have a plus and a minus. And I'm looking at factors of 3 are 1 and 3. Factors of 105 are, isn't that 105 would be 7 times 15? And then it would also be 21 times 5. So how can I multiply and subtract and get 44 using some of those combinations? If it's possible. It may not be. And I guess the other one would be 35 and 3. 35 and 3 would be the other pair. I don't think so. Because that'd be 45 minus that would be 38. That's too small. That'd be 63. That's too big. That would be, yeah, no. To me, it's going to be decimal stuff, right? Is that looking like it to you guys? Is it looking like none of those factor pairs would work with 1 and 3 to get to multiply and subtract and get 44?
Would this be calculator active?
This probably would be a calculator active, because you're going to have to go to the quadratic formula, is what you're probably going to have to go through and do, is what's going to happen. So to me, now we go quadratic formula. We can get stopped. We don't have to do that, but that's now where we're stuck with. We're going to have to find the quadratic formula. Faster way would be to plug, if it is calculator active, instead of doing the quadratic formula, plug this into y1, plug that equation into y1 and graph it and see where are the zeros. That way you can find them more precise, is what I would do on a calculator active on that one. But it is letting me know that, hey, there are going to be some crazy decimals, is what it's going to end up being, okay? All right, let's take a look at number 4, because number 4 is on the next page, so we want to make sure we do that one so we can reuse the equation. 2 towers are 30 feet apart. One is 12 feet high. The other is 28 feet high. All right, so let's draw a tower. That one is 28 feet. That one is 12 feet. All right. There is a stake in the ground between the towers. So somewhere there is a stake. We don't know if it's halfway or not, but somewhere there is a stake between the 2 towers. And there is a wire tied to the ground that goes to the top of each tower. And so that's that little diagonal line that I drew in. So here's our wires. Here is wire 1, and there is wire 2. Where should the stake be placed to use the least amount of wire? So we want to minimize the wire, is what we want to minimize. Well, so let's let A equal wire 1 plus wire 2. Okay, so again, just so we don't have to throw around a whole bunch of crazy letters in here, let's just pick some arbitrary letter like A and let it equal to the length of wire 1 plus the length of wire 2. So when we write our equation, we can use A equals as we go to do stuff. Question?
Can we do that on the test?
As long as you define it. Okay, as long as you define what your variable is, let A, because what happens when I get to teach you in this next part after Christmas, we do what's called U substitution to help us find antiderivatives a little bit easier. So you have to state let U equals this, and then you show your work with the U in there, and then you substitute back in what U is equal to, and then you finish up. So as long as you define it, yes, you can. Okay, and that mainly deals with like your free response. When you're showing your work for free response, defining what your variable is. Okay, so now, how many of you have thought the process of, hey, we got like Pythagorean theorem maybe because we got some triangles going on here? Okay, now I'm thinking the same thing. We could use trig, but they don't give us any angle measures. Okay, so we could have some stipulations using trig on this one or alternative problems doing trig. So, but let's go ahead and connect the bottom across the ground. And now what we have to do is, we know the lengths on the bottom are two different sides. So what you have to do is now pick which side do you want it to be x. You want it to be the bigger side or the smaller side? Doesn't really matter, because the other side is going to be the opposite. So I'm going to let the smaller side be x. That forces this other side to be 30 minus x. And the reason why it's 30 minus x is because they tell us the two towers are 30 feet apart. Okay, so we let one side be x, the other horizontal side be 30 minus the x. We now can go through and figure out, okay, what is the length of W1? We can say that W1 is equal to the square root of 28 squared plus 30 minus x squared. Because again, Pythagorean theorem, W1 is our hypotenuse, so basically W1 is going to be equal to the square root of the sum of the squares of those two sides. We know W2 is going to be equal to the square root of 12 squared plus x squared. Now, we can clean this up, but we know basically our function A, which is W1 plus W2, the total amount of wire, that is equal to now those two square root things together added. So whatever 28 squared is plus 30 minus x squared, that's a crazy x. And then we have to add the square root of 144 plus x squared. I went ahead and multiplied that out, just because we should know what 12 squared is. 28 squared you may not know, which is okay. And then now we would look at finding what A prime is. Now we're going to look at what A prime is. And again, the next page actually has us finding this one as one of the examples. So you want to continue and find out what it is, since we already got it prepped, ready to go, don't have to recopy? All right. So now your choice, if you want to square out the 28, multiply out the 30 minus x quantity squared, and clean that up on the inside, you can. Okay, which is not a bad idea to go ahead and do that. I think I did it on my paper here. 28 squared, I believe, is 784. So we have 784 plus 30 times 30 is 900. And then we have a minus 60x and then plus an x squared. And the other one just gets to sit and just wait, because it's already simplified. We're the way we need it. I'm going to clean that up one more time. Let me take rid of the A prime up there as I simplify those things a little bit. So my final A equation, we're going to say 1684 minus 60x plus x squared, and then plus square root of 144 plus x squared. Just side note, am I allowed to add those two things right now together into one square root? I agree with Jeffrey and Garrett. I agree with you shaking your heads no. All right. Remember, if there are multiplying square roots, we can combine the stuff on the inside by multiplying it, but we're not allowed to add those two things together and combine them in any form or fashion or subtracting. Okay, so now let's take the derivative. And again, it may help you to rewrite it with the 1/2 power, if that helps you. So I'm going to rewrite it with the 1/2 power. 1684 minus 60x plus x squared, all to the 1/2, and then plus 144 plus x squared to the 1/2. And then now let's take the derivative. A prime equals, bring down the 1/2, times, copy the inside, 1684 minus 6, wee baby, too fat of a 0, 60x plus x squared. Now to the negative 1/2. Am I done on that part? No, what do I have to take now? Thank you, Garrett. Derivative of the inside. So times negative 60 plus 2x. That's the derivative of the inside. Now I'm ready to go over to the other thing. Plus 1/2, copy down, 144 plus x squared to the negative 1/2 times the derivative of the inside. That one's smaller. It's just 2x. So I'm going to rewrite the square roots in the bottom of a fraction is what I'm going to go through and do on the right-hand side here as I clean it up. So a prime equals 1 over, but then I have a plus and then a 1 over, and it's really 1 times some stuff. So on the bottom I get to put the square root of 1684 minus 60x plus x squared. Then I get to put the negative 60 plus 2x after the 1 on the top, so it's 1 times that. And then the next one, we get to put a 2 down there, sorry. 2 in front of that because we had a 1/2. Then the 2 there, I caught that on the next one. Square root of 144 plus x squared. And then on top we have the 2x. Going to keep that close so I don't make any goofy mistakes. Now, I have to set that equal to 0. And again, I'm looking at this. I'm looking at negative 60 plus 2x over the bottom. I went ahead and reduced the 2's out. Now, this one gets to be crazy. We're not doing it by hand from here on out. We now need to go to Y1 and see where do we have our zeros. All right, that's what we need to do now, okay? Again, you don't want to do it by hand because, again, when we had one fraction, it was okay to say, oh, we got to pay attention to the numerator. That's all we had to worry about. What made the numerator 0? But since we have 2 fractions with unlike denominators, I don't want to get like denominators. Okay, that would be extremely ugly. Okay, and so, well, let's use the calculator. Let's type that into Y1 carefully, and then see where are the x-intercepts on that graph. Okay, so I'm going to try to split screen here and go in and continue. All right, let me see if I can find where I got my... I'm going to catch up to you eventually. You just keep going, okay? Again, this is a booger. This would be definitely a calculator active problem. Okay. Oh, but I don't want that calculator. I want that calculator. What do you mean TI calculator is not supported on this device? I've used a TI freaking calculator the whole dang time. What the heck? I mean, really? All right, so let me see if I can get this typed in. So this is going to be ugly on this thing. Quantity numerator would be negative 60x. Oh, no, not 60x. 60 plus 2x. Close it, divide by, on the bottom, 2 square root, inside the square root, 1684 minus 60x plus x squared. If you see me do something wrong, you better holler. Don't let me get this thing all typed in. And then plus, again, give me a fraction of x divided by, on the bottom, square root of 144 plus x squared. Okay, and hit that, and it didn't graph it. Let's see. So somewhere in here, again, you guys are, this is where the TI calculator would help tremendously. Once you get it in there, after you graph it, hit second trace, and then choose zeros. And then you'll go to left and right side of where you see a 0, and then you say, guess what that is, and it'll tell you what the x value is. Garrett, question.
No, I didn't have a question. I was just
Oh, you had the answer? Okay, cool. Thanks for getting that for us. What is the x value? It's approximately what? 9? Exactly 9? Oh, sweet. How about that? Such an ugly problem has a pretty nice answer. All right, for us to test. I guess if I kept zooming in, it would look like, hey, it's right there at 9. So now we test 9 on both sides. So I would test 0, and I would test something a little bit bigger. Again, this one, if we test values, if I put 0 in there, I should get a negative answer. Why would I get negative? Well, what does the second value? What does the second fraction do when you put a 0 in for x? What? Yeah, it makes that whole. If I put 0 in for x, that goes away. And if I put 0 in up for this x, that's negative 60. So this is a negative fraction. So I know I'm negative on the left side. Okay. So I know that's negative. And then when I put 11 in there, I know the right fraction is positive. Is 11 too close? I'm trying to do mental math, which may not be good. If I put 11 in there, the top's going to be negative. The bottom's always going to be what? Always going to be positive. So then it's going to be a matter of, is this going to be smaller? I guess this is going to be smaller than what the right side is going to be, is what I think. If we did the math, if we put like 11 or 12 or something in there for the x, and we end up doing it, yes, the first fraction is negative, but the second fraction is going to be a lot bigger of a decimal. So when we combine the two things, it'll be a positive answer. Okay, so therefore we have a minimum at 9. That'll help us minimize. Now, we're looking at the first derivative graph. What does it do at 9? Does the y values change signs as we connect our stuff that we did the last couple days? On the derivative graph, do we go from negative to positive? It's hard as hell. It's hugging the x-axis really close. But if I zoom in, let's let this take over the whole thing. If I zoom, I don't know which way is the best way to zoom, but more or less as I look at it, if this is the derivative graph, I'm negative to the left of it for all the values of 9, for the y values. As soon as I cross 9, now all my y values are positive, and so when I go from negative to positive on the derivative graph, then that indicates there's a minimum at that location. Okay. So, all right. Scooch that over. Scooch back here. So x would need to be 9 is what it needs to be. So that tells us now we can go through and figure out, well, what's the length of wire? Now we can go through and say, all right, let's put 9 in for x. So for W1, we would say, what is 784 plus, put 9 in for x, 30 minus 9 squared. So that'd be 21. So 784 plus 21 squared is 441. And then I got to square root that. So what's the square root of 5, 2, oh shoot, that's nice and easy. Isn't that 35? All right, and then now I would go to the other side, and I know it's 9 by 12, so that means that's got to be 15. So the minimum amount of wire that I need is 50 feet. 50 feet would be the minimum. Okay. That worked out to be nice. Two Pythagorean, the Pythagorean triple, just multiples of it. Any questions on that? Let's skip over to 511. Okay, again, it'd be real fast. We just did one of the problems all the way out. Okay, so there's not much less for us to do. So on 511, did we solve out that one all the way yet? Did we solve that one out? I said, you know what, we'll pick it over on this one because I said, well, let's give us more room. So let's grab that one here. We said we had square root of x minus 5 quantity squared plus x. That's what we're ready to take the derivative of. Yo! Yeah, I'm moving too fast for it. It just can't keep up. Actually, I think what it is because I am recording at the same time as doing this, and I'm moving too fast, and it just cannot keep up with the switching of stuff is what it's doing with the Wi-Fi. The Apple TV can't keep up with it. With me recording and doing it at the same time, it confused the heck out of it and stuff. So, because right now I am literally on OneNote, even though you don't see it up there. I got to keep going because we got Lindsay on this one and stuff on the video and stuff. I got her on the video here to do it. So copy down with, now you get to go auditory. Okay, you got to go old school. The video cut out. You got to listen as we do it. We said our equation. Our equation was y equals, or sorry, d. D was the thing what we're doing. See, now it's catching up. D is equal to the square root of x minus 5 quantity squared plus x, I believe is what we had there. All right. Eventually it's going to get there on the screen. It just, So we need to go ahead and find the derivative of this. Now, if you want to multiply out x minus 5 quantity squared, I'd go ahead and multiply that out. So I'm going to rewrite this as d equals square root. It would be x squared minus 10x plus 25 plus x. Okay, again, it's catching up to me. Again, inside the square root, after squaring out x minus 5 quantity squared, it's x squared minus 10x plus 25 plus x. So now I have d equals the square root of x squared minus 9x plus 25. Now let's take the derivative, d prime. That would be 1/2 times that square root stuff, but it's to the negative 1/2. So that's technically now to the negative 1/2. And then I have to take the derivative of the inside, which would be 2x minus 9 is what the derivative of the inside would be. And then I'm going to rewrite that. I'm going to clean it up. It's going to be d prime equals, on top, 2x minus 9. On the bottom of the fraction, 2 square root x squared minus 9x plus 25. And then now we have to set that equal to 0 and solve. So if I set that equal to 0 and solve, I only have to worry about the numerator. What makes the numerator 0? Well, 2x minus 9 equals 0. So 2x equals 9. X has to equal 4.5. And then now I can test. We can't just assume it, we got to test. Okay? We test 4.5, so we test on both sides. So with that in mind, if I take, I can technically take 0. If I put 0 into the derivative graph, if I find d prime of 0, then we would have negative 9 over 0 to be square root of 25, it'd be negative 9 over 10. So that means that's going to be negative on the left side. If I choose something bigger, I could choose 5. I could choose 5. If I choose 5, because that's technically bigger, if I do d prime of 5, that would be 10 minus 1 on top over basically a positive number is what's going to happen down there. So that's going to be a positive over a positive. So that's going to be a positive on the right side. So this is a min. So that is the minimum value. What point is the closest to 5, 0? Well, it's the point 4.5, comma, square root of 4.5. That is the ordered pair that is the closest. Because again, it said what point, which means I need to label the ordered pair. It didn't say what x value, it said what point. So that means I need to make sure I label the entire ordered pair. That should come up in a second or so, is what should happen. And as that's coming up, if you want to get a head start on number 3, that'd be our last problem we got to do in the practice. That's the last one of the practice stuff. Okay. And again, it's there's my 4.5 comma square root of 4.5. You know why it's going slower? We're definitely past first lunch, which definitely means what's taking place right now. And of course, exams. So that's probably where we hit a little bit of a slowdown with me recording, with me doing that. The Wi-Fi is getting a little bit splotchy because of that. Because I've recorded during a class streaming before, and it's never been this slow. I've done it for stats, and I've done it for college algebra. But I bet you that little extra bit of information on the platforms are slowing some things down too. All right, so a particle is traveling along the x-axis, and its position from the origin can be modeled by that equation, sweetness, where x is in centimeters, t is in seconds, on the interval for 3 to 9. So just going to make sure we remind here, they're giving us a closed interval for the first time. So that means we need to do that last step of step 5, where I talked about testing the endpoints too. Okay, so we need to make sure we do that on this problem as well. So they want us to figure out when is the particle furthest to the right for part A. On the same interval, what is the max speed? Okay, that's fine. So here we go. If there is my x of t, well, v of t, the velocity equation is x prime of t. You can use either notation. If you want to use v of t, since they gave us the distance equation or position equation, then we can use v of t for the derivative. If you want to use x prime, you can use x prime. Again, sorry that you have to just wait for me to get it to catch up there. I take the derivative, I get 3t squared minus 30t plus 72. I now need to solve for my values. So I'm going to set that equal to 0. I'm going to divide through by 3 to start off with to make it easier to factor. So I'm going to divide through by 3. That gives me 0 equals t squared minus 10t plus 24. That was a heck of a lot easier to factor. That means it's t minus 6 and t minus 4. And therefore my two t values are t equals 6, t equals 4. Those are my potential max and mins. But again, this is a closed interval. So now what I need to do is I need to figure out what x of 3 is x of 4, x of 6, and x of 9. I need to test the endpoints and the two critical points that I just found. Okay, and eventually that's going to pop up on the screen there. So I have right now those 4 things listed, and now it's a matter of going into doing stuff. So I'm not going to split screen because it messed stuff up. But remember how I showed you guys that you could put that equation in for y1 and then press second window and change it to ask the independent variable?
Yeah.
And so that's what I'm going to do right now, is I'm going to put that into y1 and then put in those 4 numbers for it to figure it out for me real fast. Okay, so y1, we're going to type in and x math down to 3, and then it's minus 15x squared plus 72x minus 9. All right, so I got that in there. Second window, go down to independent, tell it to ask it. And then now go ahead and go over to second graph to the table. And then we put in our numbers, 3, 4, 6, 9. And when it was 3, it was 99. When it was 4, it was 103. When it was 6, it was 99. And 9 seconds, 153. When am I furthest to the right? Furthest to the right when t equals 9 seconds. Because it has the biggest value. Now, can we get an idea of like how this thing is moving? Is it moving in a true linear fashion? No, maybe it's doing something where it's, it's going up and down, because we see it went to 99 or 99 to 103, back to 99, now back to 153. Okay, so, and I'm sure if we graph the original, we hit graph, we would see this cubic function doing what we're doing there. So, on the same interval, what is the particle's max speed? When we're trying to find speed, what do we have to make sure we do? It's been a while since we talked about speed. We always associate speed with the velocity, but in our world, we technically need to do what to it? Anybody remember? It's Jeffrey? Yeah, we got to find the absolute value. Speed is the absolute value of the velocity. Okay, so with that in mind, when we use the terminology speed, it's the absolute value of the velocity. All right, so we need to make sure we take the absolute value of it. So now with that in mind, let's find v prime of t. And so we're going to find v prime. That gives us 6t minus 30. By doing this, when I find v prime and I set it equal to 0, what does that time represent? What is that value? When I said, again, we found v prime is 6t minus 30, and eventually we're going to set v prime equal to 0. So 6t minus 30, so 30 equals 6t, so t is equal to 5 seconds. So what does 5 seconds represent in the context of this problem? Jeffrey?
This speed's not changing in 5 seconds. It's not like
So let's think about derivative y. If I take the derivative of velocity, I technically get what? Acceleration. And when I set the acceleration equation equal to 0, it's the change in acceleration. So it's almost like I'm finding that change in concavity when we're doing the other stuff. So we're changing when we're kind of doing from the negative to positive, positive and negative. So we're seeing there's a change in what's taking place there. All right. So there's our t, there's our value. We're going to do the same thing, but we're going to plug our numbers into the v equation. But we got to use the endpoints. So we found the one value on there. We got to plug them into the V equation because we're doing velocity. And the key thing we want to make sure is we want to take the absolute values of those. We want to make sure we're finding the absolute value of those things because then we're saying speed. Okay? We want to take the absolute value. Again, if you want to, you can put the velocity equation in for, we can put it into, you can put it into Y2. If you want to go into Y equals, and in Y2 put the derivative, which was 3x squared minus 30x plus 72. And then now I can go back to my table, and the only thing I need to do is add the 5 to my table because I had 3 and 9 in there already. I can add 5 to it. And then I noticed that 5, it's technically the absolute value of negative 3, which is 3. Then this would be the absolute value of, I believe that they're just 9, and that's 45. So that's just 9 and 45. And so where is the particle's max speed? Same thing, still happens to be at that. That's max speed. Max speed. The key thing is not forgetting that we're doing the absolute value stuff, okay, on the speed. So at 9 seconds, max speed of 45, what is it? We doing feet? Centimeters per second. So max speed of 45 centimeters per second. Okay. All right, so again, the first part, 5, 10, you're just writing, all you're supposed to do on that part is get it to where you get through step 3 and you stop. So it's creating the equation, rewrite it to where it's one variable, and then, get it to a standpoint where you're ready to take the derivative. You don't have to do that on that first page to take the derivative and solve. You can if you want to. The second assignment that we're on right now, that set of notes, we're doing the whole process. Okay, and then figuring out where these things are occurring. Okay, so we will turn you loose.